The next topic in light and how light behaves like a wave is polarization. So, polarization of light waves is where we get one direction for the light. Whenever we produce light, the light comes off in all directions and is generally unpolarized. So, that means the electric field, there's a magnetic field too, but here we're just going to look at the electric field, can be pointing in any direction, and that's what we call unpolarized light. This light wave comes in unpolarized, and we can linearly polarize. We can also circularly polarize and parabolically polarize light, but we're going to just stick in this class with linear polarized light through a linear polarizer. And that means that only the parts of the wave that can get through the polarizer need to be in the same direction as the polarizer. So it basically cuts the wave down in half, where the rest of the material, since we can't destroy it, is absorbed by the material. So these materials are typically dark and will warm up if you expose them to light. So this is called selective absorption, where we're going to absorb it, but the other ways of polarizing are by reflecting and scattering, which are the two topics we're also going to talk about. So how does a polarizer work is that the polarizer takes the unpolarized light and only lets the electric field that's in the one direction, or part of the electric field, so it'll let in this part and this part and this part of the electric field through it. So it's going to cut down the intensity of our light quite a bit, because not all of it is going to get through. And we can additionally remove light if we take first our polarizer, then we can take our analyzer and turn it with respect to our polarizer and take out additional intensity. The process of polarization was discovered by E.H. Land, and he discovered material that polarizes light, and so he called these a Polaroid. And these were developed much more before the company Polaroid was invented, and they kind of borrowed the name. So some molecules readily absorb light whose electric field is vector parallel to their lengths, and then transmit others. So what's going to happen is, if we have two paralyzers where they have the same orientation, you let the light through, it's not affected. But as we start to turn the polarizer as with respect to each other, the analyzer, we can completely black out the light. So the selective absorption occurs when we put it through the first polarizer. The first polarizer takes out half the light. It's just the rest of it absorbed, only half of it gets through. And then when we take our second polarizer, analyzer, and turn it with respect to our first one, then we have a different relationship, that we're going to look at the cosine of the angle between the two. So if they're pointing in the same direction, the cosine of the angle is 0, the cosine goes to 1. Whereas if these two polarizers are perpendicular to each other, then the cosine of 90 degrees is going to go to 0, and none of the light is going to get through. This is known as Mall's law. And where we use this? Well, we use it lots of different places. And so here you can see that we have these two polarizers at 90 degrees, and it's completely dark. But what interesting phenomenon is, when we put a third polarizer in here at 45 degrees with respect to the other ones, we actually do get light. So this is 3 polarizers, and we get more light than if we just had the 2. And so why does that occur? We're going to do some math with that. So here's linearly polarized light, and you can actually get circularly polarized light because light has momentum. So if you get it turning through a half-wave polarizer, you can actually get it to start spinning and rotating. The colored glass, I think, typically has circularly polarized light. Applications, there's lots of applications for polarized light. Here you see photography, where we can see a much clearer image if we put a polarizer on the camera. We also use it in organic chemistry to look at optical activity. So there's chiral molecules in there. LCD screens also use it, and so sometimes you can't see the screen because of sunglasses. I have a camera and sunglasses, and so sometimes I'm trying to take a picture, and if I rotate the camera to the vertical position and I have my sunglasses on, I see nothing, black. Whereas even if I have a slight angle on my glasses, you can see that it's dimmer than the image without the glasses, but you can still see the image. this indicates that both my sunglasses and that LCD screen are both polarized, and here we happen to have a 90 degrees difference between those two polarizers. Okay, so now we're going to do some math. Here we know that what comes out of this is 23 watts per meter squared. And so what that means is we want to find out how much light is incident on here. My equations are that I1 is 1/2 I0, and each of the other ones is the cosine squared of theta. You'll notice that there's 30 degrees difference between each one of these polarizers. So that means I1 is 1/2 I0. For the next polarizers, I2 is I1 times the cosine squared of theta, and I'm just going to call the theta is equal to 30 degrees. So this is I1, and I could substitute in I1 there is I0 over 2 times the cosine squared of theta. Then I3 is I2 times the cosine squared of theta. And I can substitute in what I2 is. That I get I0 over 2 times the cosine squared of theta times cosine squared of theta. So I get I0 over 2 times cosine to the 4th of theta. I4 is equal to I3 cosine squared of theta. So then I get I0 over 2 times cosine to the 4th of theta times cosine squared of theta is equal to I0 over 2 times cosine to the 6th times theta. Okay, so now I have an equation with what I want to know. I want to know this. I know this is 30 degrees, and I know this. So I'm going to rearrange this equation. I0 is equal to then I4 times 2 over the cosine to the 6th of theta. And that gives me, we put that all together, 109 watts per meter squared. As my final answer is how much light came in. Okay, so that's working the problem backwards. How do we work the problem forward? Working the problem forward, here I know that my incident light is 100 watts per meter squared, and then how much light do we then get through each one of these analyzers? Again, I1 is equal to 1/2 I0, so that's 100 over 2, so 50 watts per meter squared. So that means here I have 50 watts per meter squared. And then I2 is equal to I1 cosine squared of theta. So that's 50 watts per meter squared times cosine squared of 45 degrees. For this happens to be 0.5. So I2 is equal to 50 times 0.5 is 25 watts per meter squared. So that's 25 watts per meter squared, and we know that that's 45 degrees as well. So coming out this side is half of that is 12.5 watts per meter squared. So here's the math worked out that we get out of the last one, 12.5 watts per meter squared, when the two analyzers are 45 degrees with respect to each other. But if we had used in this equation 90 degrees and we didn't have this polarizer in the middle, we would have gotten 0. So actually putting the polarizer in the middle makes us get some light through that system.